Hey guys, wanted to go over a couple of these problems with you. 36 in particular because it was so lengthy of a problem. But I wanted to at least kind of go through the process with you. They're definitely not all this hard. This was the toughest one in that group of problems. But I wanted you to at least see the process so that you could apply this to any of the ones before it, like 35, 34, 33, 32. Those would be good ones. Those were easier versions of what I'm doing right now. So I figured if I could show you the hardest one, then you could then apply this same process to any of the easier problems. Here's what was going on. They gave us the original function, looked like this, and then they gave us a line that looked like this. And what they were asking was for the equation of a tangent line that was parallel to that line right there, to that one. Okay, so keep in mind, first things first, anytime you're looking for the equation of a tangent line, you need three things. You need a slope, you need an x-coordinate, and you need a y-coordinate, right? Because if you have a point and a slope, you can then plug this into the point-slope formula and get the equation of the line. So those are the three things that we're trying to identify. The slope we can get right off the bat because they said it was parallel to this line. Well, what's the slope of this line? If you put it into slope-intercept form, it's really easy to identify that your slope is negative 1/2. So there's our slope. Now we have to come up with an x-coordinate and a y-coordinate. And this is where the hard part came in. We don't know either one of those, and that's what makes this tough. If I don't know either one of those points, I can't work with the original function, at least not right off the bat. Right? I have to do some further work with the derivative because all I know is the slope. And remember that slope represents derivative. Whenever you're finding the derivative of a function, you're finding the slope of a function. Right? Derivative is slope. And so if all I know is the slope, I got to work with the derivative. So what I did on this was I said, okay, here's our function. Let's go through this derivative process where I do f of x plus delta x minus f of x over delta x. Right? That's the process that we would use, at least at this point in the chapter, to find a derivative. Now with this one in particular, there was a lot of complications with this. You got the radical, you got the fraction, and that just made this one so much harder. But understand that this is the process I wanted you to be able to use. Is if I, at this point, before we start learning the shortcuts, if I want to find the derivative of this, I'm using the derivative process, which is basically the slope process, right? This is y minus y over x minus x. And so you could then apply this to any function. This just happens to be a very tough one to work with. But anyway, so here was the setup. And again, initially we're looking for where the change in x is approaching 0. And so we can't plug that in initially. You can't do direct substitution for obvious reasons. So we go through the process of saying, okay, let's start simplifying this and see if we can't get us to a point where I can use direct substitution. Okay, so that's kind of the goal here. So what I did was I said, well, obviously this is a complex fraction. So the general process for a complex fraction is let's multiply everything by the lowest common denominator, which would be this and this, so that we can simplify it. Right? We want to turn our complex fraction into a simple fraction. So this is where the process got really tough. If you were doing the same formula but with a simpler function, this would not be nearly as lengthy. But this is, like I said, was the hardest one in the group. So anyway, so I multiplied these to every term that you see here, and here's what that came out to look like, was this next line. Oh, sorry, this line right here was the result. Right, so again, you guys remember the process on this. Hopefully from Algebra 2, these guys would cancel. So I just get 1 times this on top. Here, these would cancel, and I just get 1 times this on top, and so that's what created the numerator. And then I multiplied both of these to him, and there's our denominator. At this point, we got to go to another process where we multiply by a conjugate in order to clean up some of this. Right, so I'm multiplying now by the conjugate to top and bottom, something we've done earlier this year. And after you multiply those two together, this is what you get, this big fun fraction that you see right there. Right? So after multiplying by the conjugate, notice I did not distribute on the bottom. I I kept it all, right? It's all there. I didn't just do any distribution. On top, as you multiply a minus b times a plus b, remember that you always get a squared minus b squared. That's our difference of squares formula. If you simplify the numerator, a lot cancels out. This is all that you're left with. And I didn't want to rewrite the denominator again because it was so lengthy, so I just drew the arrow. So the denominator hasn't changed yet at this point, but what I wanted you to see is now I can do some cancellation with these guys and just be left with -1. And now I can do direct substitution where I plug in a 0 for this guy and for this guy, and here's all I'm left with. Right, so at that point I can then do direct substitution, plugging in 0 for delta x, and here is what we now have. So now that it's been simplified, I did plug in. So from here, technically this is now the derivative, but that's a complicated form. Let's clean that up a little bit. So I multiply these two together, that drops the radical. This plus this gives me 2 of those. I then rewrote this, instead of with a radical, as a 1/2 power, so that I could combine these together, right? Because anytime you multiply common bases, we can add their exponents. So I did 1 plus a half to get 3 halves, and now we're done. So this is now the simplest form of our derivative. So where do we go from there? So with this one, keep in mind we identified up top that our slope was -1/2. And remember that a derivative is a function for slope. So in other words, I can now set my derivative equal to my slope to solve for x, right? So that's why we had to go through this process to get the derivative, is because all I knew was the slope, and so I had to be able to get my derivative function, set it equal to my slope in order to figure out what our x coordinate is. And that's what we're going to get out of this here as we solve it. So right off the bat, so you could cross multiply, you could do whatever helps you solve for x. I already know that if my numerators are equal, then my denominators have to be equal as well. So I know these are equal. So I'm going to divide both sides by 2, which gives me x minus 1 to the 3/2 power equals 1. I could then raise both sides to the 2/3 power in order to cancel him out. Well, 1 to the 2/3 is still 1. So I am left with x minus 1 equals 1. Add that 1 over, and voila, we have our x coordinate. And once you have an x coordinate, how do you always get a y coordinate? Plug it back in, right? So let me go back up to this. We now know our x coordinate is 2. If I put a 2 right there, 2 minus 1 is 1. The square root of 1 is 1. 1 divided by 1 is 1. So I now have my point, I have my slope. So at this point, you could plug this information into the point-slope formula to get the equation of your tangent line. So that's what number 36 looked like. Again, guys, the main thing I really wanted to highlight on this was how do you find a derivative, right? So recognize the things that are needed in order to write a tangent line. And then understand that if all I know is the slope, I'm going to need the derivative of this function, which is this process right here, where I do f of x plus delta x minus f of x over delta x. And then from there, typically you're not going to get ones this complicated to simplify. They would be much friendlier, but I at least wanted you to remind you of the process that we use in order to get that derivative, and then what we can do with it from there in terms of setting it equal to your slope.